We are now at the point in our integrals career where we begin to focus on learning a bunch of rules and techniques for finding integrals. So we're still finding indefinite integrals. And at first glance, this problem looks quite different from our power rule problems from the last lesson, right? But what we are going to do in this lesson is essentially rewrite them to make it so that they use the same technique as before. So we're rewriting this in a more familiar way. I'll show you what I mean, and you're going to like this since you mastered the last lesson, and this is pretty much the same thing. So I'm going to divide this all together, and I'm going to rewrite it in several steps. You don't actually need to do this in your work, but I want it to be super clear what my logic is here. So the first is just rewrite how I'm showing my division. So dividing the whole thing by x squared is the same as dividing each individual term by x squared. Okay. Then I'm going to consolidate each term so that it only has one x in it using my exponent rules. So for example, I'm doing 4 minus 2 here, subtracting my exponents, and I get 24 x squared. Here, my x's cancel out, right? I'm just left with minus 7. And then here, plus 7, and I'm going to write it like this. 7 to the times x to the negative second power. Okay, so when I move that exponent to the top, the sign changes. And now I have a power rule problem. So now I'm going to anti-differentiate by adding 1 to the exponent and then dividing, right? And I can check each term, so I can check, is the derivative of 8x to the third 24x squared? And the answer is yes, so I've done it correctly. This is just a constant, so 7x. And then here, be careful with your signs. You're still going to add 1 to the power rule, which here makes the exponent a smaller negative number, right? And then I'm going to divide by that negative 1 to get negative 7. Okay, so that is my solution, and then I'm going to add plus a constant to represent whatever constant might have been in this original derivative, or original function rather, that when I took the derivative disappeared. And then, just to make this look nice, I'm going to rewrite this as 8x to the third minus 7x. Sometimes we don't like the look of that negative exponent, so I'm going to do over x on the bottom. Let's see. In the delta math examples, they are written like that, like rewritten with the x on the bottom. I'm not sure if it wants you to do that or not, but on the AP exam, it would be fine to leave it like that. So maybe do that on delta math, but don't worry about it in the long term for the AP exam. We'll do just one more example and you're going to be good to go. Okay, again, we have an integral. Does not look like what we saw before. And actually, if we try to find this integral, finding the integral of two things being multiplied together is often very challenging because there's no power rule for integration. Some of those more common derivative rules just don't work in reverse. Luckily though, what we can do is we can just multiply this together and then integrate. So we might use a Punnett square here if you wanted. Many of you can do these in your head now. So these two integrals are equivalent, and then I distribute my x, right? And then I have a nice power rule integral, so I'm going to integrate, add 1 to the power, and then divide by it. Here I get a fraction, that's okay. Here I get x to the third, and then 7 over 3 is my coefficient. And then here I get 6x squared over 2. And then I add a constant. And then it's nice to simplify, right? Again, in the AP exam, you don't have to simplify fractions and things like that. But if this were, say, an application problem, it might help us to simplify this now so we don't have to look at that 6 over 2 in the rest of the course of solving the problem. And that's it. That's your indefinite integral.